Hi everyone, in this two-part video we're going to introduce the law of cosines and its proof. So here we have a triangle with these angle theta, and A and B are two adjacent sides and C is the opposite side. So if you happen to be looking at this angle over here, B and C will be two adjacent sides and A will be opposites. So no matter what angle it's given, we can always look at these three sides relative to that given angle in there. And especially here I sketched a triangle with an obtuse angle, and here indicate that it can be obtuse. Not necessarily the law is only applicable to an obtuse triangle. So here let me put down that condition. So we have this condition that theta is an angle between 0 and 180 degrees. It can be an obtuse triangle, or it can be an obtuse triangle 0 to 90 degrees. So if you have this situation, we can write down a statement that looks a lot like a Pythagorean theorem. So we can look at this as a generalization of a Pythagorean theorem. But there is this adjusting factor in here. That's 2 times AB. 2 is always there, and AB are again two adjacent sides of that angle theta, and there's this cosine theta. It's multiplied there. So there's this adjusting factor added to the Pythagorean theorem. So C is the opposite side for that angle, and A and B are two adjacent sides. So this is the called law of cosines. So let me use this acute example to compare the result with the Pythagorean theorem. So here's this dotted line making the 90 degree with the baseline in here. The base is B, same as here, and this perpendicular line has length A. So we're going to compare this length C with this hypotenuse of this right triangle in here. But what you see over here in this additional solid line is a rotation of this dotted line around this vertex here. So the length of this one is kind of radius of this circle I'm drawing here, such that these two are the same. So I'm keeping this length, two adjacent side of the length, same, and changing just the angle that will change this side length of the opposite side. So I want you to compare this, they added here, and compare this hypotenuse with this green line, which is the opposite side of this acute triangle. It seems like intuitively, it seems like it's getting smaller. So C squared in this right triangle, the square of this hypotenuse is the sum of the square of A and a B. But in here, A and B are kept the same, and C has gotten smaller. So C squared, if you compare it, the C squared we're looking at here is not equal to A squared plus B squared. C squared, what is A squared plus B squared, is the square of this one, because that's the right triangle, and it seems like it's got smaller. So you have to get this correct quantity of C squared, you have to subtract off a little bit, and that's exactly this quantity, 2AB cosine theta. So I'm going to sketch an example where theta here is obtuse, so we're going over to the other side. So sketched here similarly, the angle theta we're looking at here is greater than 90 degrees. So this is where 90 degree and A and B. So that hypotenuse of the right triangle will make these two things equal. But if I increase the angle, this part here, a little bit, then as you can see, if you compare it with this line in here, it seems like it got a little bit longer. So, and this will make the square of this hypotenuse of this right triangle in here, but this C squared we're looking at is slightly more than that. But you don't add this factor, but we still subtract this factor. It turns out if theta is greater than 90 degree, this remains a negative number. If theta is greater than 90 degree in this case, of course less than 180 degree, that's what we started with. So in that case, this cosine is already negative. There is a negative sign out there, and together the effect of adding this negative number negative number is actually adding positive number, so that'll do the effect. So both cases, the sine negative 2ab remains the same. The sine of cosine theta we're putting in here takes care of addition and subtraction automatically. So I want you to look at this as a generalization of a Pythagorean theorem. So let us take a look at the proof and why is this theory this equation is always true.